to the Today Show. Today we welcome Monsieur Lavoisier. We're so lucky to have him, so let's give him a nice warm welcome.
Hello, Miss Kirk. Nice to meet you.
Nice to meet you too, Monsieur Lavoisier. We last saw you in May of 1784.
Oh yes, during what you now call the Reign of Terror, I was sent to the guillotine for defending the necessity of the Academy of Sciences. Those were treacherous times.
You are most likely unaware that after your death, Joseph Louis Lagrange said it took them only an instant to cut off that head, and 100 years may not produce another like it. But perhaps I should not speak to you of your beheading.
That's okay. It's been 224 years, so I've gotten over it. I appreciate you telling me. That was awfully kind.
Let's go back in time. Can you share some background information regarding your early years?
Well, I was born on the 16th of August, 1743. My father was a lawyer, and my mother came from legal stock. I received what some would call a classical education at Mazarin College, and after I studied a range of sciences, including geology, meteorology, chemistry, and botany. Although my family was involved in the field of law, I knew I had a more scientific mind.
Well, your decision to enter the field of science worked in your favor. Or should I say, you worked in its favor. So, when you finally began researching, was it in the field of chemistry?
Actually, my first few research projects did not involve chemistry. In 1763, I worked on a project involving tertiary rocks in a region of Paris. In 1765, I earned a medal for a paper submitted to a competition comparing different methods of lighting that used different types of oil to improve the efficiency of lighting in Paris.
Wow! Well, congratulations.
Thank you.
So, what did your first experiments in chemistry involve?
I first worked with gypsum, a mineral found in many trees. I used a carefully crafted hydrometer, an instrument used to measure the density of liquids in order to compare the densities of gypsum and water. My hydrometer was constructed with a closed silver container. On the bottom of the cylinder, the part that was most immersed in a liquid container, hung a specific weight of tin. On the top of the hollow cylinder was a stem with a mark. When the hydrometer was placed in a liquid, weights would be added or subtracted to a pan that set atop the stem until the level of the liquid reached a mark on the stem. In this way, relative densities could be measured.
As I understand it, after these experiments, you began working on heat and mass?
Yes, in 1768, I began experimenting with water in closed vessels. I added a known mass of water to a bulb, closed it, and heated it for 110 days at 80 degrees Celsius. A piece of earth formed in the bulb. I evaporated all the water, measured the mass of the solid and the weight of the bulb lost. To my confusion, the solid weighed more than the weight lost, so I concluded that weight was added to the solid from the glass bulb container.
Did these experiments lead you anywhere?
Well, I eventually teamed up with Macquet and Cadet in the early part of 1772. We heated diamonds in an open container and in a closed pipe. Our experimental results were such that the diamonds heated in the open container lost mass and became discolored, while those heated in the closed clay pipe only lost some of their polish. We reasoned that contact with the air, or lack thereof, affected the results.
That's fascinating. 1772 was a monumental year for you, was it not?
It really was. I truly believe that most, if not all of my experiments follow those of the autumn of 1772. You see, this is when I began burning metals in open air. I first massed and heated phosphorus in a closed container. Then I massed phosphorus after heating and observed that the mass of the phosphorus increased while air in the container had been absorbed. I repeated the same experiment using sulfur in place of phosphorus, and the results were the same. From this, I reasoned that while heating, the metal absorbs a certain amount of air from inside of the container.
Can you explain why you were performing these experiments? What were the standing theories of the time?
Before those experiments, and for some time after, most scientists believed in George Stahl's phlogiston theory. It was a common belief that phlogiston was a principle, something comparable to an element, that was found in all things. Calcination and rusting was explained by the loss of phlogiston. Burning could occur with the presence of phlogiston, and phlogiston was released into the air when the human body respired so that breathing could continue. The theory of oxygen was non-existent.
Thanks for informing our 2008 viewers. How did your preceding experiments shed light onto the scene?
Following my work with phosphorus and sulfur, I performed calcination experiments. Calcination is the process of burning metals into oxides or ashy substances. Of course, at the time, we did not refer to them as oxides. I worked with both tin and lead. I first placed a certain amount of metal into a vessel, closed it, masked the filled vessel, heated the vessel until the metal completely burned, and measured the mass of the vessel before opening it. You see, previously Boyles had performed the same experiment, but opened the vessel before massing it, whereas I masked the vessel before opening and after opening. I found that the mass of the closed vessel after heating was equal to the mass of the vessel before heating, but the mass of the open vessel after heating was greater than the mass before heating. This was reasonable to me at the time because I could hear something rushing into the container. In 1779, I was still confused by air. To be quite honest, at the time I had more confidence in phlogiston theory supporter Joseph Priestley's ideas than my own theories.
Well, when did you finally begin to fully develop your theories and put them into writing?
My biggest work was a textbook published in 1789 entitled Traité de élémentaire de chimie. Basically, the book outlines my experiments since 1772, and the topics covered include heat, composition of the atmosphere and water, and some organic chemistry. This was my first written textbook in modern chemistry, so nothing concerning phlogiston theory was discussed.
Can you speak of chemical nomenclature?
Sure. In 1787, Fourcroy, Morveau, and Berthollet and I designed a new system to identify compounds by their elemental compositions and presented the system in a paper entitled Méthode de nomenclature chimique proposée. It had been known that the metals and carbon, sulfur, phosphorus, and nitrogen were elements. After my discovery of the principle oxygen and air and subsequent experiments, it was determined to be an element. I also performed an experiment with water to determine its percent composition because water formed on metals in so many of my previous experiments. I figured if I were to find the percent composition of water, I could use the data in calculations of previous experiments to gain more insight. I used a kind of three-bulb apparatus to measure the masses of each component in water vapor. After this experiment, hydrogen presented itself as an element as well. The significance of each of the elements mentioned, previously referred to as principles, led to the formulation of a system of chemical nomenclature that could be used to describe chemical compounds and their interactions.
Today, many refer to you as the father of modern chemistry. Many say that you significantly propelled, or that you are the sole individual responsible for the chemical revolution. Do you feel that you are deserving of this credit?
There's no definite answer to this question. Those who argue I am worthy of the title accredit it to my establishing chemistry as an independent scientific discipline, though this is debatable, my theoretical approach to chemistry, and my oxygen theory. Many believe that chemistry was hardly a scientific discipline before my time, maybe a subdivision of physics. However, this is not all true. Before my time and in the early part of my career, chemistry in France was a fairly independent field in which chemists involved in medicine and industry would perform analyses of aqueous solutions and experiments involving heat, combustions, calcinations, etc. I know that this has been a discussion of debate since my passing. I wrote 2 letters to the Academy of Sciences before my election as a member, arguing for a new physique expérimentale division, and some argue that I disguised chemistry under a physics title in order to promote it as a science in an acceptable manner. Whatever the case, chemistry was an established field in science by the time of my death. Before my time, chemical observations were made, but there was less emphasis given to theory. I was not the first theoretical chemist, but I was a very strong believer in the importance of theoretical chemistry. I viewed my experiments as a way to understand theory, and this is most especially evidenced by my contributions with regard to oxygen. The transformation from Stahl's phlogiston theory to the oxygen theory signified a change from chemistry based on speculation. Those who believed in phlogiston assumed that this substance existed, to chemistry based on experimental method, which I largely modeled off of experimental physics. The combination of these things set chemistry in a whole new direction.
Okay, and if you were to give advice to current scientists, what would you say?
I would say, when nothing stimulates the working mind, when there's nothing to direct its attention to any definite object, often in an aimless course it wanders and goes astray. Its slow and delayed products perish before they have seen the light of day.
Thank you so much for your time, Mr. Lavoisier. It was very nice to meet you.
Nice to meet you too.
Tomorrow, we'll welcome renowned physicist Albert Einstein. Good night.